Hello, I'm Suba Thomas. I'm a software developer here at Wolfram Research. In a short while, I will be giving a talk on the microcontroller kit. The microcontroller kit automates the generation and deployment of microcontroller code from the Wolfram language. I have here with me a couple of examples that I will demo during the talk. It will be a very hands-on presentation. I hope you enjoy the presentation and find the functionality useful for your projects. Thank you. Good morning and welcome to this talk on the microcontroller kit. So this is going to be a very hands-on presentation. So I think a good introduction would be a demo of a basic example. So first let me load the package. And I'm also going to set the port through which I'll be uploading code to the microcontroller. Now what I have here is an Arduino Uno with an LED connected to pin 3 and a potentiometer connected to pin A0. I would like for the microcontroller to read the potentiometer value and adjust the brightness of the LED based on that. It's very easy to get started with this kit because there are only 3 user level functions and 2 of them are helper functions. The main function is this embed microcontroller code, and it takes 3 arguments. The first argument, which is this one, is the core function that needs to run on the microcontroller. In this case, it's a state space model with 1 input and 1 output, and the input is directly fed through to the output. So if I look at the output response, if I give a sinusoidal input, it's going to give me back a sinusoidal input. If I give any arbitrary input, it will return that same input. And this is what I want. I want the microcontroller to read the potentiometer value and feed that value directly through to the LED. The second argument has got to do with the target hardware. And this has 3 sub-arguments. So the first one is the name of the target itself, which in this case is the Arduino Uno. The second one is the list of inputs, and the third is the list of outputs. So each input you specify as the pin name and the configuration. In this case, it's pin A0 configured as an analog input. And then we do something similar for the output. We give the pin name and the configuration. In this case, it's pin 3 configured as an analog output. And the last argument is the port through which we will be uploading the code to the microcontroller. Now, if
what's that first argument? It's got funny formatting. What's its full form? Or
it's a state space model, so it's an input-output model. So if I do an output response, if you give any input to it, this particular one is going to give back the same output. Okay, so now if I evaluate this, it's going to upload the code onto this target. So I get the second function in this package, which is a data object, and it tells me that it has generated the source code and embedded the machine code to the target. So now, because it's uploaded here, if I now adjust the potentiometer, the brightness of the LED should change based on that. I hope you could see that. Okay. From this data object, we can get other properties. Like we can ask what was the source code that was generated. And there are a whole slew of other properties that we can query from the data object. Now this is a summary of the typical input and output channels in a microcontroller. We just looked at the analog output and analog input. Let's look at a few more. One of the basic features in a microcontroller is digital output. Here I have an LED connected to pin 4. If the pin value is high, the LED is going to turn on. And if the pin value is low, the LED is going to turn off. So to do that, I have a nonlinear state space model, again with 1 output, and it's a constant high gain output. It has no inputs, and the output is connected to pin 4. So now if I evaluate that, it should turn on that LED which was connected to pin 4. If I make it a low value, it should turn it off. Now we can extend this to get the LED blinking. For that, I create a nonlinear state space model with one state, with the state is also the output. And if the state is high, I turn it low, and otherwise if it's low, I turn it on back high. And the sampling period becomes the delay between the transitions. So now that LED should be blinking every half a second. Now let's look at something that's a bit more involved, which is SPI communication. In SPI communication, there is a master device and a bunch of slave devices. The master is responsible for the clock signal, and it synchronizes all the devices. On the MISO line, which stands for master input and slave output, the slaves are sending data to the master. And on the MOSI line, which stands for master output and slave in, master is outputting data to the slaves. At any one time, the master is talking to just one slave, and the master decides which slave it's talking to by making that slave select line of that particular slave low. So let's look at an example of this. I have this Arduino that I'm going to configure as a master SPI device, and I'm going to get data from this MAX6675 sensor, which is a temperature sensor. So all the lines you see here, these are the serial clock. This is the master input, slave output, and this is the chip select line, the slave select line, which I've connected to pin 7. Now, whenever we connect a device to an Arduino like that, we have to tell what device it is. And for that, Mbed microcontroller code has this option SPI. So under this option, we can enumerate all the SPI devices that we have connected. And so here I have only one, and the slave is uniquely identified by its slave select pin. So this will generate code to read 2 bytes from that sensor. Why 2 bytes? Because that's from the data sheet. So now we have got the data. The next thing we have to do is pair it up with an input channel. In general, we could have several slaves and several input channels, but this is the same procedure for everything. We will list the master input slave output pin, which for the Arduino Uno is the pin 12, and configure it as an SPI pin. So data is coming in through that, and then we have to say from which slave the data is coming in. Evaluate that. And then we have to say how to convert that data. Again, this recipe for converting those 2 bytes into a temperature value, that recipe comes from the data sheet. And the output I'm going to send over serial. The reason I'm doing that is because now after this I'm going to use the serial, the device framework to read the temperature back into Mathematica. So let's embed that code. So now the code is running on the Arduino. It's getting the data and it's sending it back over the serial line. So I'm going to use the device framework. I'm going to open a connection to the data. The data is coming in as integer codes. So I create a parsing function that will convert it into Wolfram language expressions. And then I set up a scheduled task, which is reading the data, parsing it, and appending it to that list. And now if I evaluate that, it's reading the temperature. I'm going to stick the end of this thermocouple into some ice, and it should decrease. Yeah, it does. So we are able to read this temperature. We are able to embed code and then use the device framework to get the temperature back into Mathematica. Now I'm going to remove that task and close the device. So let's look at the third function in this package, the user level function, that is microcontroller targets. This function will give you the list of targets that are supported. So I can query for what are the vendors whose boards we support. I can pick any one vendor and say what boards from that vendor we support. Or I can ask for what microcontroller families are supported by this kit. I can pick one microcontroller family and say what are all the boards that are based on that family that we support. So next let's look at the speed control example. Let me bring it up on the camera. Okay, so over here, I have the Arduino at the bottom. I have a motor shield in between and a prototyping shield on top. The reason I have that motor shield is to boost the power of the signal that is coming from the Arduino. During operation, the motor will be drawing much higher power than the rated value of the Arduino pins. Yeah, okay, I can show it from here. So I'm using this potentiometer here to set the reference speed, the speed I want the motor to be turning at. And that signal I feed into this analog input A5. The actual speed of the motor is measured by this encoder here at the back. And I feed it back into this digital pin 2. It's a digital signal. It's a sequence of pulses. By counting the number of pulses, we know how fast the motor is going. The more the number of pulses, the faster, and the slower the motor is going. And then the Arduino is going to compare these two values and compute an appropriate signal to send. It's going to send it on pin 11. It's going to send it on pin 11 because the motor shield pairs that pin 11 to channel B, to which I've connected the two leads of the motor. To go ahead with the control design, I'll need two models. I don't have time in this talk to go over how I derive that, but I'll point you to the documentation later. So the first model is the model of the motor. It models the speed of the motor in response to an applied voltage. And the second one is an inverse shield model. So it is mapping the output of the shield, which is the voltage that is going to be applied to the motor, to the input signal at the shield, which is the PWM signal that's coming from the Arduino. We'll see in a minute why we need that. So I'm going to use the motor's model and compute a controller using PID tune, and then discretize it with a sampling period of 0.5 seconds. Now that block, I feed it into that inverse shield. The reason I'm doing that is because this controller is computing the voltage that needs to be applied to the motor. But in the physical setup, the actual voltage is being given by the motor shield. So what this block does is it looks at the voltage that needs to be applied to the motor, and then based on that voltage, it computes the value of the PWM signal that needs to be applied by the Arduino to the motor shield, so that signal can eventually reach the motor. The input of the PID controller is a comparator to compare the two signals. So the first signal is the signal coming in from the potentiometer. The potentiometer reads a value between 0 and 5 volts. And this motor is rated for 600 RPM. So I would like to max the speed off at 500 RPM. So what this block does is that it looks at the set voltage and converts that into an RPM value from 0 to 500. And I'm doing something similar for the encoder. All these numbers come from the data sheet of the encoder. 12 is the number of pulses per revolution of the motor shaft, and it is coupled with by a gearbox to the actual output shaft. And so this product is counting the number of pulses per revolution of the output shaft, and the inverse of that multiplied by the input of this is going to give me the number of revolutions. And I'm counting those revolutions every sampling period. So this divided by the sampling period is revolutions per second, multiplied by 60 is revolutions per minute. So at this point, both the units are RPM. The long and short of this computation is that it takes pulse counts, raw pulse counts, and converts it into an RPM value. Okay. After I get all these components, I can assemble the controller, and then I have the first argument to embed microcontroller code. Now I'm going to specify the target is of course Arduino Uno, which is at the bottom. I'm going to specify the inputs and outputs. The first input is the analog signal, the reference signal coming from the potentiometer. It's connected to pin A5. The second one is the digital input that is coming through pin 2. Now there are several ways you can count the pulses. You can count either the rising edges of the pulses, or you can count the falling edges of a pulse, or you can also count the number of toggles the pulse is making. If I change this to the number of toggles, I'll have to double this, make it 24, but I just chose to go with the rising edge, so I'm just counting the rising edge, so that will give me the number of pulses. Okay. Now for the output is the PWM signal. It's scaled from 0 to 100. That's on pin 11. And so all these two inputs and this output, that's all I need for the speed controller. But I'm going to add 2 additional outputs. And the reason these are both serial outputs. The reason I add these outputs is for me to again use the device framework and get it back into Mathematica so I can visualize the set and actual speeds. So let me embed that. Oh, no. I should change this. Let me reevaluate that. Okay. So I'm going to do something similar that I did with the temperature reading. I'm going to open a connection to that device. I'm going to create a parsing function that's going to change the raw bytes that are coming in into Wolfram language expressions. And I'm going to set up a scheduled task that's reading the data, parsing it, and appending it to a list. And then I can, which one? Yeah, I think it missed a byte. Let me try this again. Okay, it probably dropped a byte when it was getting the data in. Okay, so now everything is at rest. I'm going to give it a step input, and I'm just turning the potential. I'm ramping it up. So you see this is the controller responding to the set speed. It takes some time to reach the speed that was set, but if I change it gradually, then it will do a better input tracking. So this is a metric of how good the controller is doing, how well it tracks the input. Another metric is we can give it a disturbance and see how well it responds to a disturbance. Again, if I give a gradual disturbance and gradually take it off, it's good. But if I give a sudden disturbance, it takes a while for the controller to realize. And if I abruptly take it, again, it takes a while for it to realize that there is no more load before bringing it back. Okay. Okay, so what are the benefits of using the microcontroller? So in one word, it automates a lot of things. So embedded microcontroller code does a lot of things behind the scenes. The first thing it does is it generates the source code, and then it invokes a compiler to compile that into a binary format. And then it invokes a programmer to take that binary code and passes it through an external programmer onto the microcontroller. So, most of this is also automated in other platforms like the Arduino IDE or the Atmel Studio. But the added advantage here is that we are also automatically generating the source code. So why is that important? If you look at a typical development cycle, we are getting a controller or a filter from a model, and then we are generating code and then deploying it and going into testing and verification. So anytime that there is a change in the requirements, or there are enhancements or corrections in the model, or if there are improvements in the controller or filter design, we'll have to regenerate the code. Also, if if you make some changes in the physical hardware too, it can be a tedious process to actually regenerate that code. So this adds a level of automation which streamlines the entire process. And another advantage is it generates hard real-time code. So at each sampling instant, the microcontroller is doing a bunch of tasks. And there is no control on how much time it will take to complete the task at each time. And after that, it is essentially idle except for any interrupts it will have to service. But this code, it does not depend, it does not see, it is not a delay after that. It does not see after that how long it takes. At each sampling period after that time, it exactly starts doing the whole sequence again. So we enforce hard real-time constraints in this. So in closing, the microcontroller kit enables a streamlined and uniform workflow to rapidly iterate and deploy code to microcontrollers. There are three main symbols: embed microcontroller code data, and microcontroller targets. Microcontroller code is the main one, and we have ref pages and examples for all the three. There's also several tutorial pages, and the tutorials and ref pages go into much more detail and have way more examples than I've been able to present here. We also developed several projects. I just showed you one, but there are others too. We like an analog filter realization or a line following control. In these, we list what are the parts you need, how to assemble them, how to get the model, how to design things. We go over the whole process step by step, so you will be able to replicate what we have done. Yeah, so that concludes my talk. Thank you very much.